Hello everyone, welcome to Physics Queries. Today we'll solve the problem from the Pathria book. Uh, the question mark is 2.4. So this is the question we'll solve today. So you can read the question. So basically the problem is associated with rigid rotator. So okay, so you can see there are two masses M1 and M2, and they are uh, connected with some fixed rod of r length, and there is a middle point, not middle point, there is a point based on their masses distribution. This is basically the center of mass of the system. So from the center of mass, m1 mass is r1 distance away and m2 mass is r2 distance away. So this is basically a typical figure of a rigid rotator. So if we say simply, so rigid rotator is a idealized system consisting of two point masses, or you can assume atoms or molecules, and they are connected by a fixed rigid bond. So the distance between two masses is always fixed. That's why we are using the term rigid. Actually, their bond is rigid. So the distance between those two masses cannot change. They has to be fixed. So here only the freedom is about the rotation about the center of mass. Okay. So there are no other freedom. So in this type of problem, we basically prefer to use the polar coordinates to describe its orientation. So here we'll use theta and phi orientation, and this is basically the limit of theta and phi here. Now, in classical description, if we write the kinetic energy of the system, so this is basically the kinetic energy of the system, L square by 2I. So here we are considering the potential energy of the system is 0, and here the I, which is inertia, this is nothing but mu r square, and mu is basically the reduced mass, uh, m1 m2 by m1 plus m2. So here angular momentum vector, this is conserved. Now, if we come to the quantum description, so in quantum description, so energy operator Hamiltonian is nothing but L square by 2I. If we take it as a free free potential body something. Okay, so here L is the angular momentum operator, and if you calculate its eigenfunction and energy eigenvalues, this will be basically uh, the spherical harmonics will be the eigenfunction, and energy eigenvalues will be h cat square by 2I into j plus 1. So here j varies from 0, 1 to any integer values. So here angular momentum is not only conserved, that also quantized. Now let's dive into the problem. So if we write the energy of the rigid rotator, this is basically energy of the rigid rotator. So basically here we are taking only the kinetic term. We are considering potential energy as 0. Now, if you solve this problem, you will basically get m square by 2I. Now, here, if you can solve it from the Lagrangian method. So the Lagrangian of the system is basically E minus B. So here we are considering B is equal to 0. So this is basically E is equal to L. So from that you can calculate the P theta and P phi. So basically here the P theta and P phi value will be this. So that value we have uh, used here in the energy equation, and mu is the basically I have already told you that this is basically the reduced mass m1 m2 by m1 plus m2. Now if you solve the equation, you will basically get here m square by 2I. Now m square is what? So if you compare those equations, m square is nothing but p theta square plus p phi square by sine square theta. Now if you rearrange the equation a little bit, you will get a basically ellipse equation. Now the equation format is like x square by a square plus y square by b square equal to 1. So basically this is a square and this is b square. So from that comparison, you can get this is a, this is b. Now if you want to calculate the area, this is nothing but their multiplication, pi m square sin square theta. Okay, sorry, this will be pi m square sin theta. This will not be sin square theta. Sorry for my mistake. Okay, now if we want to now we have to calculate the phase space volume. So the volume of the phase space will be, so their associated four coordinates will be theta, phi, and their momentums p theta and p phi. So v will be basically the integration of dp theta, d theta, dp phi, and d phi, and their limits we already know. So we have used the limits and we have solved this value. So we get this value 4 pi square m square. So this is basically the volume of the phase space. Now, if we want to calculate the microstate, we have to divide the volume by h square. Basically, h square is the volume of the unit cell according to our statistics mechanics convention. So here number of microstate will be v by h square. So if you solve it, you will basically get m square by h cut square. So here h cut is nothing but h by 2 pi. Now we have to calculate the microstate associated with a single cell. So to do that, we'll first uh, calculate the quantized angular momentum. So this is the allowed magnitudes for a quantum rigid rotator. Root over of j into j plus 1 into h cut, where j can take values either 0, 1, 2 or half, 3 by 2, 5 by 2 in any way. Okay. Now, if you want to calculate the count or number of semiclassical count, so that this will be nothing but mj by h cut whole square, which is j into j plus 1. So basically mj by h cut is nothing but the 2D phase space. Okay. Now you have to calculate a microstate associated with a single j. Now let's do that. Now to assign the microstates to the level j, uh, we are taking the difference between the counts of just and above the cell. So we are taking a choice that is j plus 1 by 2 and j minus 1 by 2. So we use those values to calculate the microstates. So if you simplify the equation, so basically here you have to put the value from the j into j plus 1. So this is j plus 1 by 2 into j plus 1 by 2 plus 1. So in this way, if you simplify, you will basically get the value 2j plus 1. And this is nothing but the quantum degeneracy. So in the case of rigid rotator, the number of microstate available to a rigid rotator, this is same as the quantum degeneracy 2j plus 1, where basically this degeneracy is like magnetic quantum number m equal to minus j to plus j including 0. That's why if you count them, that will be 2j plus 1. Okay, so this is our result. Yeah, thank you. See you in next video.